Hello, everyone, and welcome to this talk titled From Solar Rooftops to Power Grids. I'm Ankit, an applications engineer from the Wolfram System Modeler team. In this session, I'll walk you through a use case that highlights why simulation is essential in driving the energy transition, from understanding household behavior to designing resilient power systems. The world is electrifying, and the pace is accelerating rapidly. In the next 6 years, global electricity demand is expected to rise by around 6,500 terawatt hours, according to the International Energy Agency. To put that into perspective, that's like adding another United States worth of electricity demand. And the US is already the second largest consumer of electricity after China. This surge is driven by data centers, the electrification of heavy industries, electric transport, and other emerging sectors. But while global demand keeps growing, let's take a moment to look closer to home and see what the current reality looks like. For this presentation, let's focus on South Africa, a country that reflects the situation in many developing economies around the world. It has a growing economy and a young population, especially when compared to developed nations. However, since 2018, South Africa has experienced frequent load shedding, largely due to aging power infrastructure and insufficient generation capacity. While the situation has improved somewhat in 2025, load shedding remains a daily reality for many households. What's more concerning is that costs are rising too. Compared to 2003, the residential electricity tariff has increased sixfold. So, while people are paying more for electricity, they're actually getting less reliability. In short, bills are going up while the lights are still going out. Unreliability isn't just a theoretical concept, it has real, everyday consequences. Your fridge warms up and the food inside spoils. Your lights go out in the middle of an important task, maybe even a job interview. Or your washing machine stops halfway, wasting both time and energy. So, how do we move towards a more reliable power supply, one that's built on informed technical decisions without spending a fortune on oversized systems? Let's explore our use case through a household in Johannesburg. Before we look for solutions to improve reliability, it's important to first understand the electricity demand and identify the main contributors. Climate plays a big role here, influencing seasonal heating and cooling needs. So, let's start by gathering data for Johannesburg. Using the Wolfram language, we can easily connect to open data sources like PVGIS to extract solar radiation and temperature information for the region. Once we have this data, we can build a generic household energy model based on engineering first principles to estimate electricity demand from different sources. Now, before diving into the details of that model, let's look at what the simulation results tells us. For a 100 square meter house, the model predicts an average consumption of around 650 kilowatt hours per month, which stays fairly consistent throughout the year. The major contributors to this demand are electrical appliances, followed by water heating and space cooling. During the winter months in South Africa, roughly May to August, the demand shifts towards space heating, while the rest of the year is dominated by cooling loads. As you can see from NREL data, the electrical load, which includes lighting, cooking, refrigeration, and television use, makes up the largest proportion of household energy demand for a middle income group. This is followed by water heating and then by space heating and cooling. Now let's look at one of the submodels I use to predict space heating and cooling demand. This is a house model built in Wolfram System Modeler. Here, the thermal inertia of the building is represented using a heat capacitor component. Here, multiple heat sources and sinks are connected to it through input signals such as solar radiation, ambient temperature, and heat losses to the surroundings. We also have a controller in the model that maintains the indoor temperature. It automatically switches on the radiator when it's cold or activates the air conditioner when it's hot. In addition, there is a component that accounts for heat generated by occupants inside the house. The plot you see here shows the simulated results across 10 different years, capturing how the building responds to changing seasonal conditions. I won't go into all the other submodels now, but if you're interested, you can find more details in the link provided here. To summarize, what we have seen so far is a simulated model of a household in Johannesburg, capable of predicting energy demand based on different heat loads and climate factors. Next, let's look a bit deeper into the resulting demand profile over a span of a few days to understand how load fluctuations occur in practice. If we dig a bit deeper into our household model, we can start to observe some sharp transitions in the energy demand as shown in this plot. A lot of data contributes to these variations: heating or cooling based on temperature, lighting that switches on and off depending on solar radiation levels, and other appliance usage patterns. Still, we can identify some general trends. After midnight, the demand is mostly from heating and cooling loads. During the day and early afternoon, when there is sunlight, fewer people at home, the demand drops to a low level. Then, in the evening, we see a few distinct peaks caused by activities such as cooking, using the dishwasher, or watching television. This profile represents a typical residential load. Now, if we shift perspective and look how an energy provider views the same situation, aggregating data from homes, offices, industries, and other facilities, we see a different pattern. Such a plot usually shows two main peaks: one in the afternoon when the offices are running at full capacity, and another at night when households become active again. My current model focuses only on residential consumption, so it does not include the daytime commercial peak, but the overall trend remains similar across most regions. So far we have looked at the demand side through simulation. Now let's turn to the grid side and understand what happens when demand and supply fall out of balance. When we talk about the grid, you often hear terms like frequency and voltage. Let's use a simple model to understand why load shedding occurs. One of the main reasons is that demand exceeds supply, and as a result, the grid can no longer maintain a constant frequency. Imagine a gas turbine generator with a rotating shaft. The rotational speed of this shaft determines the frequency of the AC power it produces. In normal operation, the turbine rotates at constant speed, generating electricity at around 50 Hz. As the demand increases, the controller tries to supply more power by increasing torque. Initially, the rotational speed stays stable and the frequency remains close to 50 Hz, with only minor fluctuations as the controller adjusts. But as the load continues to rise, the turbine eventually reaches its maximum deliverable power. Beyond that point, it can't increase torque further, so it starts losing rotational speed. This causes the grid frequency to drop below 50 Hz. A falling frequency can quickly affect all connected equipment, from household appliances to industrial machineries. And to prevent that, the grid operator must shed some of the load, which is what we experience as load shedding. Now that we've understood how demand dynamics and grid stability interact, let's look at what we can do at home to manage our own power usage and even help make the grid more resilient. Let's start by adding a battery to our household model. In the same diagram that I used earlier for the grid, I have now extended it by including an electrical battery system. All the components you see in this system model diagram are built using free open libraries that are supported by Wolfram System Modeler. Once the setup is ready, I can easily experiment with different battery types and capacities, and then simulate how the system performs. In this example, I began with a 10 kilowatt hour battery, which roughly matches the daily requirement of this household. And to make the concept clearer, I simulated a simplified scenario where the grid supply is limited to 800 watts, while the household peaks at around 1 kilowatt during the evening hours, roughly between 5 to 9 pm. In a traditional setup, this shortfall would cause a power outage or load shedding. But in this model, the battery compensates by supplying the total energy during that time window. So, from this simulation, I can also calculate how much stored energy is needed to cover an entire blackout period. In this case, about 10 kilowatt hours. This kind of model can be used to explore strategies like peak saving, where you use stored energy during expensive tariff hours to reduce electricity costs. The advantage of simulation is that it lets you design and test different storage configurations before making any real investment. Now, let's move to the next step by adding rooftop solar to our system. Now, let's add a rooftop solar to our model and make the household operate independently of the grid. In this version, I have replaced the grid connection with a solar power model, which can be parameterized using real design data from commercially available solar modules. Once the setup is complete, I can simulate the system to see how it performs and whether the sizing of the solar array and battery is appropriate for my household's needs. In this plot, the blue curve shows the solar power generation throughout the day. You can see that during the afternoon, when the sunlight is abundant, the solar energy is used to meet household demand and to charge the battery. The subplot below shows the state of charge of the battery. It increases towards 1 during the day as the battery charges and then gradually discharges in the evening, reaching a minimum of around zero point 0.5 by night. With a model like this, I can now answer practical questions such as what type of solar panels are best suited for my home, what battery capacity should I choose to ensure reliability. By simulating the scenarios first, I can make data driven design decisions before spending money on hardware. This type of model is not limited to a single residential building. It can easily be scaled up to represent entire communities by adding multiple demand centers. In such a setup, the households can share energy resources, distribute their storage costs, and have solar panels spread across the community, making the system more cost effective and resilient. In the simulation shown here, you can see that after around 9 pm, the battery is no longer able to deliver the required power. The state of charge drops to zero, indicating that the battery capacity is insufficient. So, in this case, we would need to choose a larger battery. This demonstrates the true advantage of simulation. You can make a model, you can reparameterize it easily, add new components, scale up the system, and study different load patterns or configurations. You can also include realistic data such as temperature, solar radiation, and household demand to test a wide range of operating conditions. Beyond that, you can even simulate fault scenarios, for example, during maintenance periods or unexpected outages, to answer practical questions like how much backup power is needed to meet the demand, what happens if one subsystem goes offline. And by doing this virtually, we make well informed, low risk decisions about how to design and manage reliable energy systems, from individual homes to entire neighborhoods. To summarize what we have explored in this presentation, we saw how load shedding disrupts daily life and how simulation helps us understand and solve this challenge step by step. We used models to study household energy demand, simulate batteries to find the right size, and integrate PV systems to achieve greater reliability even during blackouts. We then extended the same approach to community scale systems, showing how one model can be reused and scaled to design grid independent neighborhoods. In short, we saw how simulation makes scenario testing easy, helping us make smart, data driven energy decisions before making real investments. In this presentation, we moved from grid dependence to grid independence and ultimately to the idea of grid support, where households not only consume power but also contributes to grid stability. Simulation empowers us to make smarter design decisions and helps us make the right energy choices for our homes and communities. Thank you.